In lab 12.2 we are going to look at signed arithmetic, and specifically we're going to build a 4-bit signed adder. Okay, so in the last lab, lab 12.1, you may recall that we created a unsigned adder, and we did this by using the plus sign that was contained within the numeric std library. So it was pretty simple because what we ended up doing was, since we couldn't use the plus sign operator directly on the inputs, which were of type standard logic vector, we had to actually convert them to unsigned and then perform the addition. So in order to facilitate the sum being unsigned in this situation, we had to create an internal signal which was of type unsigned, and then what we did is we just casted A and B to unsigned, and then we added them together. We did an additional step to kind of make this easier by actually making the sum 5 bits and then making each of the inputs 5 bits by concatenating a 0 so that we could easily track the carry out. Okay? And so all we did was, after the sum, we took the lower 4 bits of the unsigned adder, casted it back to standard logic vector, created the sum, and then we took the 5th bit of the vector, and that was simply cout. In this situation, we are going to use the type signed to perform the addition, but what's beautiful about the way that VHDL treats these numbers is that all you have to do is change the type of your internal sum from unsigned to signed, and then you are good to go. Okay, so that's all that needs to happen. The plus operator works exactly the same regardless of whether you're using signed or unsigned. However, it is important now to, instead of making the sign or making the internal sign 5 bits, you want to keep it 4 bits. And that's important because we want to look at the negative or positive value of the inputs and outputs. And if you recall, that means that we look at the most significant bit. So by taking this and concatenating a 0 to it to make this 5 bits, that doesn't work anymore, because what we've done is, even if A was a negative, we would have changed it back to a positive. So in this lab, what you want to do is you want to do your operations on only 4-bit values. Okay? And so you want to have the input be 4 bits and the output be 4 bits. And then what we want to do is we want to display this on the character decoders, but we want to indicate whether something is negative, and the way we want to do that is we want to actually have a negative sign. So the whole magic of this lab is really all about creating a decoder which can create the actual negative sign. Okay? Now if you think about that, you're going to have a 4-bit input that's going to be displayed on hex 0. You're going to have a 4-bit value that's displayed on hex 2. And then we're going to use these additional hex character displays to just simply either be off, indicating it's a positive number, or make the middle LED light up, indicating it's a negative number. Same thing, we will put the sum on the hex 4 display, and we will put a negative on hex 6. So in reality, it's very simple. These values right here are just going to come straight from the 4-bit inputs and the 4-bit sum. And if you look at the block diagram, all we're going to be doing here is looking at the inputs, switch 3 to 0, that's where the first input will come in, and then switch 7 to 4, that's where the second one will come in. We're going to have an assigned adder. This again is just a simple process. We don't even need to do concatenation or anything like that. The internal sum can be 4 bits wide, and it can be signed. And then the inputs, or excuse me, the output, sum, and the 2 inputs are all 4 bits, and they're just going to be driven basically straight through a card decoder. However, you are going to need to have the ability to drive a negative sign to the neighboring card decoder. So what you should do here is create a 2comp decoder component. And if you think about what's going to happen here, is this is going to be a new component, but highly leveraged from your existing component, that's the card decoder. And you're basically going to create this new component, this new file, and it's going to look at a 4-bit input. It will drive 2 hex displays though. One of them is just going to be simply, one of them is going to be driving hex 0, and the other one is going to be driving, let's say, hex 1, for example, for these two. The negative sign is simply just going to look at the sign bit. If the sign bit, or the most significant bit of this 4-bit code, is going to be a 1, that means light up this middle LED. If it's a 0, turn them all off. You can implement the logic for the sign display simply with an if-then statement. Okay? This one, though, is a little bit different because it's not a straight decode of the value of the straight binary value like we had in our card decoder. So what you have to do is you are going to make a case statement that is going to convert all of the 4-bit codes coming in on this input, and you're going to figure out the correct number that should be displayed here. Now this is very simple for a 4-bit code. You're either going to have, for example, you'll have 1000, that's going to represent the value -8. Okay, and then 1001 will represent -7. So for those codes that are negative, you have to actually change the values that you drive to this hex display to make it accurate. So that's why you need a different card decoder, because the binary codes no longer represent unsigned symbols. They are signed symbols. So you'll put the magnitude of the symbol here, and then you'll put its negative sign there. So that's the majority of this lab, changing the process to signed and reducing the inputs and the output to 4 bits, not that big of a deal. Creating a new card decoder for the input, the 2 inputs, and the sum, that's going to take a little bit of work. And then the last piece of this, though, is we want to create an overflow flag. So we want to add some separate logic, which is going to be another process that is going to look at the addition here and figure out if overflow occurred. We want to display that overflow flag on LED 9, the red LED in position 9. And if you think about how you're going to do this, your circuit right here really only needs to look at the most significant bit of the 4-bit input here, which is going to be switch 7, and the most significant bit of the input here, which is going to be switch 3, and the most significant bit of the sum. The reason that you're looking at the most significant bits is because those are the sign bits. You are going to create logic here which will say, hey, I'm adding, and if I ever add a positive number to a positive number and I get a negative number, I'm going to have 2's complement overflow. Or if I ever add a negative number to a negative number and I get a positive number, I've got 2's complement overflow. Otherwise, I don't have 2's complement overflow. So that logic right there can be easily implemented with an if-then statement or a case statement, and you only have these 3 bits in there. Remember, this process is separate from the adder process, totally separate. It actually has to wait until the sum is computed, but that's okay, it'll happen very fast. So these are 2 separate processes, and this process right here is combinational logic. So combinational logic right here is going to need to look at these inputs in the sensitivity list. Okay, so this is what the actual lab looks like. You're going to have the switches right here, which you flip in the codes for the input here, and then flip in the codes for the input here. The sum will be displayed here. As always, you'll put the values of the switches directly on the lower 8-bit LEDs, and then display 2's complement overflow on this most significant red LED. Okay, so your deliverables for this, I also give you the entity for the 2's comp decoder just to keep everything kind of consistent. If you look at the deliverables for this, the first deliverable is going to be a video, 90%, that just shows the proper operation and make sure of your design. Make sure to show a case where you have a couple positives adding that are correct, a couple positives adding that result in 2's complement overflow. You'll see the overflow flag asserted, and you'll also see that the value is wrong. And then also show the case where you have 2 negative numbers added together and the result is okay, and 2 negative numbers that are added together and the result is not okay, and the 2's complement overflow is asserted. That's 90% of your design, or of your deliverable, and then of course 10% is uploading your top.bht, and that is going to be lab 12.2.